Okay, let's get started. Last day we introduced visual testing via the lineup test. And this is a significance test just like any other formal significance test you've encountered in the past. It's just that the peculiar thing here is that the test statistic is a graphic and you're a part of the test statistic itself. So you're part of this discrepancy measure. So we've got null hypothesis, a test statistic or discrepancy measure. We can generate values under the null hypothesis. We know how to generate values, and we can get a significance level just by whether or not you pick the actual data. Things we notice, different people perform differently, and that just means that as part of the test statistic, you can improve your performance with a little practice, right? Understanding the graphics, what to look for in terms of differences, etc. Also noted that different graphics perform differently. In particular, the quantile plots, for example, perform better than the back-to-back densities. Although the back-to-back densities perhaps may look aesthetically more pleasing, they don't seem to be as powerful a means to detect the differences that we looked at. The other thing is that the graphics have different features that they're chasing. You know, for example, that box plots are not very good at chasing modality, how many modes there are in a distribution, or distinction in the number of modes. They are pretty good at looking at location and scale and assessment of symmetry under the assumption that there's a unimodal distribution that generated the data. So some graphics are going to be better at detecting certain differences than are others. We want to employ graphics that make the most sense or doing the best job for detecting these kinds of differences. So today I want to focus on particular departures, right? I want to focus on particular hypotheses of increasing specificity. So, for example, here are a number of hypotheses that we might consider in comparing two groups of data, or even looking at comparing two groups of data. The one we looked at last day is that there was a common distribution generated both sets. That is, each set of data looked like it was generated by an independently and identically distributed generation from some particular distribution. We didn't specify what the distribution was, but we're asserting that they came from the same distribution, whatever that distribution might be. And that allowed us to say, well, if they're from the same distribution, we should be able to mix them up randomly, and the graphics should not change very much. Well, we could get more specific than that. So oftentimes we're interested in really the shape of the distribution. And by shape, I mean pretty much anything that has got nothing to do with where it's located or how spread out it is. Nothing to do about its location and scale, just the shape. So I'm thinking about multimodality, weight of tails, symmetry, asymmetry, etc., but not location or scale. So oftentimes I wonder whether or not they're from the same distribution and they only differ by location and scale. Okay? Another possibility is that I've specified the distribution itself exactly up to a location and scale. So for example, I may say that perhaps the data look like they come from a normal with some mean and some standard deviation, but I'm just not saying what they are. I don't really care what they are, but do they look normally distributed? And I might say that do they come from some particular parametric family? Right? You often have parametric families when you're doing statistical modeling. Do the data look like they could have been generated by that family? And that could be indexed by some parameter, or in fact have that particular parameter specified. Okay, so the entire distribution might be specified itself, or some parts of it are specified and some are not. Okay? So the idea is looking at that's an increasing specificity from the most general hypothesis we had last time, that they come from the same distribution, to particular constraints on the distribution. They're the same up to location and scale, et cetera, or they're completely identified. So we could adapt our lineup test to generate data from a particular distribution to meet any of these conditions. And all we need to do is figure out how do we generate the suspects in a new way. Rather than just mix randomly, we need some other way of generating the suspects. So let's consider this hypothesis. The hypothesis is that they come from the same shape distribution. The data sets may have different locations, different scales, different means, different standard deviations, however you want to measure location and scale. Okay? So under the null hypothesis, we could transform the data so the two data sets have the identical location and scale, and then we just want to compare them. The remaining comparisons, since we've matched them on location and scale, should be just about the shapes of their distributions. Okay? Everybody with me? All right, so how might I match that? So I'm going to match them using some robust estimate of location and scale. I'm going to use the median for the estimate of location and the interquartile range for the estimate of scale. And so I'm going to write a function here that's going to take data, and remember our data abstraction that we have, it has two named components, an x and a y. Those are the two different data sets. And I just want to match them. And I'm going to match them so that they have identical median and identical interquartile range. Median will be 0 and the interquartile range 1. So that's all this function is doing this rescaling and returning another named list, okay, of data. And the data that comes back are exactly as they were before, except now they have median 0 and interquartile range 1 for each of x and y. Okay? So if I want to test that hypothesis then, I need to begin with some data. We're going to look at the body temperatures of those two beavers. So I'm going to match those data on their median and interquartile range. So now they match on location and scale. And I want to call our lineup test. We'll do the back-to-back density, see how those work for assessing this. So I'm just matching location and scale. And now the function of generated suspect, I'm going to randomly mix the data as I did before, but again, match them, make sure that they've got median 0 and interquartile range 1. So any differences I perceive in the two back-to-back densities will not be due to location and scale. Okay? So what's that look like? So there we have it. So I've matched them on location and scale. So the median temperature is the same in both of these. The median range of interquartile range of temperatures is the same. Which of these look least like the others, or which has the pink looking least like the blue? So have a look. I'm going to want a show of hands in a moment. See if you can pick one that you think they look least alike, or that graphic looks least like the other 19. Everybody got one? Okay, let's do a quickly show of hands high. And 1, nobody. 2, one person for 2. 3, 4, one person for 4. 5, 1, 2, 3, 4 for 5. 6 for 5. 10, 9, 8, 7, 6, 11, 12, 13. Whoa. 1, 2, 3, 4, 5. So keep them out. I don't know, it looks about tens of people for 13. 14, 15. Anybody not voted? So nobody picked 20, 19, 18, 17, or 16. So the bulk was for 13. So let me just see if I can evaluate that. Of course I can't now that I'm using Adobe. Pardon me while I just pull up this thing again with a preview so I can cut and paste this. So here we are here. Are 13. That's what most of the people picked, but there were other people picking other values. So that, I think that's where most people picked, right? Was 13. Yeah. So we can, they got a significance level of 0.05 for those that picked it, and for those that did not, there's no evidence against that null hypothesis. So let me get back here. All right, so we could do the same again with quantiles. So if we look at quantiles, it's exactly as before. I'm going to mix the data and then match the data, and use quantiles instead of back-to-back. And now, which of these is less like the others, least like the others? So they should lie on top of each other if they're identical, the blue and the pink. Quick show of hand, everybody got one? Anyone got one? People have one? Okay, 1, 2, 3, 4, 5, 10, 9, 8, 7, 6. Everybody has one? 11, 12, 13, 14, 15, 20, 19, 18, 17, 16. So unanimity, everybody picked 18, and for sure that is the difference. So somehow we've got, everybody is able to pick this out with this particular graphic. So the quantiles on top of each other seem to be more powerful than the back-to-back densities, even when we're just looking at the shape. So that's good because I'd already typed that clearly the quantiles were better. So I'm glad you guys picked that. So now the idea is, well, what if that hypothesis was a little more focused? Not just, any shape, but what if it was a specific shape? So what if I was interested in, for example, it came, whether the data, just think of a single data set for the moment. Does that data look like it comes from a Gaussian distribution, from a normal distribution? With some mean and some standard deviation, I don't care what. Right? So specifying the distribution shape. It's not that two sets have the same shape, which we've already looked at. A single set, does it have a Gaussian shape? Does it look like it's plausibly from a Gaussian? Or some other distribution? Does it look like it's plausibly from a student on T-shaped on some number of degrees of freedom? Right? With, location and scale. So I can relocate and scale a student like I can any other distribution. And oftentimes you have a statistical model that's assumed some particular distribution for the data, and you'd like to assess that. So what we need to do is compare the data against data from that distribution, but make sure that that data from the distribution matches the data that we have in hand in terms of location and scale, because we don't care about those differences. So the hypothesis here now is a little narrower. We've got some specific distribution, some specific shape in mind, right? But we don't care about location and scale. So now I have a function here that's going to take an argument, r dist, which is some function that can produce a sample from that distribution, whatever the distribution is that's of interest. Default here will be the normal or Gaussian distribution, so we can use the built-in function r norm from R. So what I'm going to do is when I get matched data, I take the data that's coming in, I generate a sample of the same size from whatever that distribution is, and then I make sure that I match that new data to have the same median and the same interquartile range as the original data, okay? So get matched data just goes, get some new data from that distribution and make sure you match it on median and interquartile range. So let's look at the beaver temperatures again. And let's take X to be the temperatures, body temperatures for the first beaver. And so our data is going to be X is that value, Y is just going to be something from that that's normally distributed of the same size as X and matches on the median and interquartile range. Okay? So that's the data that we're going to look at. That's the data we want to be able to recognize in any lineup plot. So again, we can use back-to-back densities here. And what happens when we generate a suspect, we're just going to get matched data on whatever the X and Y that is that comes into it. Okay? So I'm going to generate it from a normal distribution. That's the default. But it could be any distribution if you provided it. Everybody understand that? So it's a small modification. I'm just giving it a different function for generating the suspect. Everybody with me? Okay. Which of these doesn't look like the others? Trying to assess whether that temperature looks like it's normally distributed or could have been generated by a normal distribution with some mean and some standard deviation. So which of these looks least like the others? Everybody got one? Everybody have one? Okay, pick one. Do not be swayed by the peer pressure. So let's go from the bottom. 20. 1, 2, 3. 19. 18. 1, 2, 3, 4, 5, 6, 7. 17. 16. 11. 12. 1. 13. 14. 15. 1 for 15. 10. Couple for 10. 9. 8, 1, 7, 6, 1, 2, 3. Okay, lots for 3, 4, 5. Okay, so we saw a fair variety there. Again, I'll have to pick this up from the preview. So what was the most popular one again? 3. 20. You guys lose. 20. So the people that their hands shot up first, you guys won. There's 3 or 4 of you. L. So either there's no evidence against the hypothesis that these could have been generated from a normal distribution, or the statistic, including you, was not powerful enough to detect it. Okay? So on the basis of this test, the great bulk of the folks here decided there's no evidence against the hypothesis that that body temperature looks like it could be Gaussian. Okay? So let's do this with quantiles. Same thing with quantiles. So I'm just displaying these in different ways. Now you're to pick which of these show the greatest difference from each other. And keep in mind, I'll be trying to match these on location and scale. So we'll pick one. Are we ready? Okay. Everybody got one? Okay, let's try, let's start at the bottom again. 20, 19, 18, 17, 16, 16, 1 for 16, 11, 1, 2, 3, 4, 5, 6, 7, 8, oh, it's a snowball. 1, 2, 3, 4, 5, put your hands up again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 13-ish. 12, couple. 13, 14, 15, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, again, about the same as we had for 11. 9, 8, 7, 6. 1, 2, 3, 4, 5. Some of you are voting twice, aren't you? 1, 2, 3, 4, 5. Okay, so contenders were largely 10 and 11, I think. It is. So more people picked 11 there than picked the correct answer 20 in the previous one. Same data, same problem entirely. It may look like, again, the quantiles may be a better way to look at these data. And for many of you, there's no evidence against the hypothesis. Although I'd venture to say that if I asked you to pick 2 plots, we might have had a lot of people picking 10 and 11. Which, you know, if it's one of those two, you think I can't choose between them, or then you reduce your significance level to 1 and 10, but you've still got something happening there. Okay. Right. So, if I wanted to look at any other distribution, all I need to do is define that distribution. So if I want to say, does it look like it comes from a t distribution on 3 degrees of freedom with some location and scale, I just have to write a function that will return that and give that to the layout, the lineup function. So again, back to back with these, we'll just go through these quickly. There it is, comparing it with a t on 3 freedom. Any of these jump out at anyone? Could you pick one? Very quickly. 1, 2, 3. If you can't pick any, don't vote, okay? 4, 5, 1 for 5, 10. Couple for 10, 3 for 10, 9. Few there. 8, 7, 6, 1, 11, 12, 1, 13, 1, 14. It's the winner so far. It looks about 8 or 10. 15. Also about half dozen. 20. 19. 18. 17. 16. All right, now I'm curious. I don't know the answer. But it looks like that might be a little hard to tell here. 5. Nobody picked 5, I don't think. So that looks like no evidence whatsoever against the hypothesis that these could have been generated by a student on 3 degrees of freedom. So again, with quantiles, have a look, pick one. Got one? I know I'm rushing you, but got one? Okay, 20. 1. 19. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 18. Nobody. 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and again. 16, 11, couple, 12, 13, 14, 15, 10, 9, 8, 7, 6, 5, 4, 5. Somebody picked 5. One person picked 5. 2 people picked 5. Can I ask you why? It's kind of like 19 here. Okay. 5 or 3? Why 3? Don't they look kind of on top of each other, the number 3 here? Okay. 4, 3, 2, 1. One person for 1? Okay. So hopefully we're doing a little better with this one, he said, because we missed completely with the other one. 18. How many people picked 18? Nobody picked 18? Really? I'm pretty sure I counted people that voted for 18. This is recorded. I'm gonna have to go back and look at that. I was sure there was 10 of you guys that picked that. Hell. Okay. So one of the problems with what we're looking at, both of those they weren't that good, right? Arguably, in some cases, we had the quantiles were doing a little bit better than the back-to-back, but in both cases, it was kind of messed up. So either there's no evidence, or yes? So the question is, how do I come up with a log formula? It's completely out of thin air. I just had to encode it some way that you couldn't immediately recognize it. You could do it in a million different ways, right? I just don't want you to be able to mentally be able to take that apart and get the answer. So any way that obfuscates it will do. Okay, so one of the things that we have there, we were comparing the data itself back to back or against the quantiles of data randomly generated. And then doing that, comparing that to pairs of randomly generated and randomly generated. And it seems like we've got one too many randomly generated things in there. Like, why do we care so much about comparing the data to randomly generated as opposed to comparing the data, like pairs of data randomly generated or pairs of randomly generated? Can we remove one of those sources of variation, the random variation? So what I want to do is compare the data that I have to some real good measure of the underlying hypothesized distribution when I've got something that specific, okay? And to get that, we need to think about how would you recognize distributions? And I want to tell you that each one has its own signature. And we can think of that signature in 3 traditional ways. One is the density, here in the leftmost plot. The other is the cumulative distribution function. And the third is the quantile, the inverse of the distribution function. So we've been using this and this. So when I look, this is a normal 0, 1 density. It has that canonical, unimodal bell-shaped curve. And its CDF also has this canonical shape, and its quantile function has a canonical shape. This is what Galton called an ogive after the architectural feature. Okay, that kind of shape is classically for a normal or Gaussian distribution. If I look at a uniform distribution, it's some rectangle as the density. Its CDF is easy. It's just this y equals x line. Right? The probability of being less than or equal to a half is a half. probability of being less than or equal to 0.75 is 0.75. It's a uniform distribution. And the inverse of this is also, the quantile function is also this straight line. Okay? And you can look at lots of different distributions. So the beta distribution gives us a variety of shapes. So you can think about what do you see in one of these pictures and what does that correspond to in the other. So if I see this density, what does the distribution function look like? What does its quantile function look like? And so the beta, you've got this unimodality, has this, it's kind of like an ogive, like the Gaussian one, but not quite the same. When I get this beta and I get to have tails coming out, it is starting to look more like the shape of a Gaussian quantile function, just as its density is looking a little bit more like a Gaussian. If I have skewed densities, here's a beta, so skewed with the long left tail piled up on the right. Its distribution function is not much probability of being less than or equal to that value, and then suddenly a lot. And its quantile function has this also distinct curvature, and you think again that horizontally flat spots, or the flatter spots, are where it's piled up the density more, and these vertical spots is where the density is spread out. So this vertical spot here corresponds to the density being spread out on this side. Okay? So you're going to need to practice and sort of think about what does this shape that I see over here correspond to there, and vice versa. If it's skewed in the opposite direction, well, the vertical part where there's less density appears on the right-hand side. So this right tail is light. Okay? Here's a beta 0.1.1, which looks, you know, pretty flat, and then it's got these spikes at either end. So you see that what happens here is that there's a lot of probability being spread out here at the ends. A lot of the probability suddenly is piled up at the ends. You get a ton at the beginning of the CDF, and then sort of kind of uniform looking, and then you get a ton at the right-hand side. The quantile function, there's a mode there. You see how flat it is horizontally, and a mode at that end, and then it's spread out in between. When I get beta 0.9.9, there's enough probability inside here that this thing's starting to look almost like a straight line. There is curvature there. So it looks kind of like a straight line, means it looks kind of like a uniform. That is, for the great bulk of it, it looks uniform, but there is curvature that's curving up and curving down, just like this does here. But there's so much of it in the middle that looks kind of flat. Again, there is curvature there, you just can't see it. So that quantile function looks a lot like a uniform quantile function, but it isn't. It's got curvature there. So if I make these things more skewed, so that it really piles up, you'll see that there's greater curvature, and always in one direction. So it's skewed in one direction or the other direction. And all you have to think about is where is it spread out. So it's spread out in this tail here, which is the right tail. It's spread out in this tail here, which is the left tail. And similarly for chi-squared distributions, also skewed. You can see as chi-squared degrees of freedom increase, it's definitely very skewed out so that the right tail is very thin, and that skewness changes slightly as the degrees of freedom increase. And as that degrees of freedom goes to infinity, this will start to look more and more like a Gaussian distribution, as we see here. So this is a chi-squared, for example, on 30 degrees of freedom, and that looks kind of like an ogive, kind of like a Gaussian. So these curves are all related. They're different signatures of the distributions, and you should be able to recognize from this density what should the quantile function look like, what should the distribution function look like, or from this quantile function, what should the density look like. Okay? When we get to very, very heavy-tailed symmetric things, so here's a t on 1 degree of freedom. This is the Cauchy distribution. It is so strange that it has no finite moments. So it doesn't have an expectation, although it obviously has a median. That would be a good value for the location. And you see here it looks like a Gaussian, but really exaggerated. Very long tails, lots of it piled up, lots of probability mass out in the tails. And as degrees of freedom increase, you get closer to Gaussian. If you've got bimodality, as we saw with the geyser data, you're going to see in the quantile function this, where it's thin, a mode, thin, mode, thin. So you can pick off the, when you see that kind of quantile function, you know that there's bimodal density. Okay? So the idea is, if we've got that information, we know quantiles, for example, we could use the theoretical quantiles. How do one set of quantiles compare to the other set of quantiles? It's a little difficult looking at these various shapes and distinguishing them one from the other. But the beauty of a quantile function is that they have the common x value, right? They have a common value p here. So I can match, for any p here, I could find the corresponding value on either of these quantile functions and compare them. So I could have for the distribution of x, it's theoretical quantiles for any p. For the distribution of y, it's theoretical quantiles for the same p, and look at that pair of points. That is a quantile-quantile plot, or QQ plot, which you've seen in other courses, but we have not seen yet here. What we've been looking at is the pairs p, q, y of p, which is a quantile plot. Now, turns out that what we've been looking at is also a QQ plot if you're imagining you're comparing it to a uniform, because uniform quantiles are just p. Okay? But that's a distinction between a quantile plot and a quantile-quantile. And I'm just not going to look at any data here. I would just want to look at what are the actual values of these quantiles. How would I compare these distributions? So, for example, if I have identical distributions, in the top left corner here, I've got the quantiles for uniform 0, 1 on this axis versus the quantiles for uniform 0, 1 on that axis. I'm going to get y equals x line perfectly. Okay. That red square that I have there, that red rectangle, is always the unit square on the scale, just so you can see where the unit square is comparing these. Top right, I've got the quantiles on the horizontal axis for a t on 3 degrees of freedom versus a t on 3 degrees of freedom. Again, a straight line. It's the same distribution. They got to match. Here I have normal 0, 1 versus normal 0, 1, chi-squared 3 versus chi-squared 3. In every instance, when I'm matching identical distributions, I'm going to get a y equals x line. That's where that curve is going to be. It means it's a perfect match. Okay? Well, what if the only difference between these variances, they come from the same distribution, but they have different locations in scale? So x is from some distribution, whatever you choose, and y is just a scale and location transformation of x, which means it has the same shape distribution. Well, if I look at here, on the top left here, I have a uniform 0, 1, the quantiles, and on the vertical axis, I've got a uniform 1, 2. Uniform 0, 1 versus uniform 1, 2. All I've done is I've shifted, right? I've changed the location. I've added 1 to everything. That's all I've done. And the effect is, instead of going through this box from corner to corner, as it would if they were identical, it's got the same slope, but its intercept has changed. Because all I've done is added 1 to everything. So B is 1 and A is 1. Haven't changed the scale, just changed the location. That turns into changing the intercept. Here I have uniform 0, 1 and uniform 0, 10. So what have I done? I've added nothing to this, but I multiplied everything by 10. And what you see here is still a straight line, goes through the origin, but has a different slope, slope 10 instead of slope 1. So provided they have the same shape and they only have different location and scale, all I'm going to get is a straight line, but with a different slope and intercept than I have for the when they're identical. Okay? When they're identical, I'm going to have an intercept 0 and a slope of 1. So from looking at this line and seeing what the slope and intercept of that line is, I know, if it's a straight line, I know it comes from the same distribution, and it's just got a different location and scale. For example, this is a normal 0, 1 here, and here's a normal 4, 1. So I've added 4 to everything. Normal 0, 1, normal 0, 4, I've just multiplied all the scales by 2. Okay? So the beauty of this is that if they have the same shape, you'll see a straight line. Okay? So if I'm interested in looking at comparing a data set to a target distribution, all I have to do, or looking at comparing two different distributions, because I want to look at first at the theoretical quantiles, all I have to do is get this two sets of quantiles and look at the resulting curve. If it's a straight line, they're coming from the same shape distribution, and the slope and intercept tell me about the particular change in location and scale. So what you've seen a lot is we're going to look at compared to a standard normal, normal 0, 1. So let's make the horizontal axis will be the quantiles of a normal 0, 1, and then we're going to look at the quantile function for a variety of other distributions on the vertical axis. Okay? So, for example, I have normal 0, 1 across the horizontal axis here, and on the vertical axis I've got the corresponding quantiles for a Cauchy distribution, a t on 1 degree of freedom. And what do you see? Well, it's not a straight line. It's not the same shape of distribution. In fact, compared to the normal distribution, the distribution on the vertical axis has much heavier tail on the right, because it's got more things spread out on the right, more spread out on the left. In the middle, if you imagine chopping that off, that looks a little bit more like a straight line in the middle. That's that single mode in the middle where they're mostly agreeing. And of course, if I did chop that off, I'd see more curvature again just from rescaling. So when I see this, I know the thing on the right, on the vertical axis has heavier tails. It's got more in that tail. There's more, that tail stretches out more. Okay, the tail stretches. Yes? Yes. Yes, so if you see this happening, you can see that there's more probability out here. If you think about it, imagine, just for the moment, imagine there's a straight line there. So this is assuming that the two distributions agree. If this one was really normal, I'd expect its value to be somewhere along that line. In fact, it's much farther away from the middle, right? So its values are way farther out in the tails. So it's got more probability mass out here than does the normal. Yep. It's the same as before. When we were it's the same interpretation as quantile functions before, except quantile function, if you think about it, on the horizontal axis was the uniform. So I'm comparing everything to a flat uniform. Now I'm comparing it to a Gaussian distribution. If I look at a t on 3 degrees of freedom, it's the same story, that it's got more weight in both of these tails than you'd expect to see than the Gaussian has. These are the actual theoretical values, so it has more tail weight out there. Not nearly as much as a t on 1 degree of freedom. So as the degrees of freedom increase, it's going to look a little bit more like a Gaussian. In fact, on 10 degrees of freedom, that's the comparison of the quantiles, which is not a straight line, which means it's not identically shaped, but it's very similar. It's got, again, slightly heavier tails on both sides than does the normal distribution. Okay? Make sense for everybody? Sometimes it's helpful, and this is just choosing a convenient straight line so you can see where the departures are. So I add this straight line here so that you can see that it is farther away from where I would expect it to be for a Gaussian. It's farther away from the middle there. It's farther away from the middle here. Okay? So this difference is largely in the tails. And just repeating myself here, if they'd been identical, you'd expect that the y values would follow along that red line to agree with the x values. Here's a number of other examples. We're looking again, putting them all together, T1, T3, T10, and I think that's T30. So by the time you're up to 30 degrees of freedom, that looks a lot like a normal distribution, except in the very far tails. Okay. So whenever you look at normal tables that are tabulated, sometimes they stop tabulating them at 30 or 50 degrees of freedom because they look just like a normal, except farther out in the tails. So that looks a lot, that T on 30 degrees of freedom is very close to a normal distribution. And in fact, as you know, as the degrees of freedom goes to infinity, it is exactly a normal. Similarly, we can look at a chi-square distribution. So this is on 1 degree of freedom, 3 degrees of freedom, 10, and 30. And of these, the one that's most looks like a normal distribution is this one, but it's still clearly different. I'm going to look at the most exaggerated one here, and I've got this red line there. So if where I expect the Gaussian to be is on this red line, and on the right-hand side, the chi-squared is way farther away. That's that long right tail. It's farther away from the middle. Over here, this red line on the left would continue down here, and if it was Gaussian, I expected that curve to be down here, but in fact, it's much closer to the middle. That's a shorter left tail, right? That it's flat there, that mode, compared to what we see in the Gaussian. So if I expect it to be Gaussian, I expect that curve to be down here, but in fact, it's much closer to the center of the data, or center of the distribution, rather. Okay? So you should be able to look at these curves and say, how does this compare to the normal distribution in this case, or compared to the distribution that I have on the horizontal axis? Again, this is mixtures of distributions. Mixtures of distributions, it's easy to tell compared to a normal distribution. We've got two modes here. Okay, so there's some separation, there's some spread out here in the middle compared to the distribution of a normal distribution, compared to the density of a normal distribution. So multimodality shows up very nicely with this curvature here. So it looks like, it's almost like it looks normal there, and then it looks normal again here, but something shifted, that the intercept is shifted, so that's a change in location. Okay, so we've got a normal, change location, another normal. Okay. So, we just get to something here that's familiar then, is those were actually looking at the distributions comparing themselves mathematically one to another. What we have in fact are data. And so what we might look at is we've got the quantiles, the theoretical quantiles from the specified distribution, but we also have the empirical quantiles. What are the empirical quantiles? That's just the sorted data, right? Y of I, right? It's just the order statistic. And to make them match, we're going to do this little fudge factor. I minus a half over n will be the p-value, so that we're not trying to match on 1, for example, which we know is off at infinity. Right, so we're going to subtract off a little bit so we can match on values that are not too far out in either tail. So if I look at the geyser data, for example, there's your classic normal QQ plot, which you will have seen, and it has that thing of a bimodal distribution. So immediately looking at this, I know it looks kind of sort of normally. Then another piece here with this low density piece in the middle compared to what we'd expect for a normal distribution. I think I've asked you, everybody has seen QQ plots and normal QQ plots. So now you think back to those theoretical things, these signatures here, that's what it would be in theory for that geyser if there was a bimodal distribution generating it, and what you actually see in practice is this. Of course, the other thing you see in practice before I leave this is this flat part at 4 and 2, which is clearly a measurement problem. Somebody's just measuring the duration to the nearest 2 minutes or 4 minutes. They're saying that's 2, that's 4. They're not being very careful. Okay, till next day, we'll pick it up there.